All right, so welcome to my series of videos on statistics. And in this video, I'm going to teach on estimating or estimations and hypothesis testing for two population proportions. All right. Now, here, we are going to talk about how to estimate or how to even test hypothesis involving two population proportions. So earlier, in some way in the series of the videos, we were taught how to test hypothesis for proportion when it is only for one group. But in this video, we are going to test hypothesis for proportion when it involves two groups. So here, first of all, the confidence interval for proportion when it involves two groups is that for every confidence interval, remember, there will be a point estimate plus or minus the critical value times the standard error for every proportion. So when we have two population proportions, the point estimate is the sample proportion of the first one minus the sample proportion of the second one. So this is the point estimate, okay? This is the point estimate. All right, so this is the point estimate. And this is the critical value. And then everything here is the standard error. Okay. Now, remember these formulas carefully. Now, if you want to test for hypothesis when it comes to two population proportions, it means that definitely, remember when I was teaching you proportions, the critical value of a proportion is always the z because there can be no t in proportion, all right? So remember, if you are anytime you want to do a particular z value, remember this is how we do a z value. So for every z value, remember for every z value or for every critical value, let me put it in that way, for every critical value, it is the point estimate minus the population parameter divided by the standard error, all right? Now, when it comes to proportions, the point estimate for a proportion is the sample proportion of the first group minus the sample proportion of the second group, okay? And almost always the population parameter is 0, okay? That is the population proportion minus of the first group minus the population proportion of the second group, which is almost, so always we hypothesize this to be equal to 0, all over the standard error of the proportion, all right? So when it involves two proportions, okay, the standard error of the proportion is square root of sample proportion of the first one into bracket 1 minus sample proportion all over sample size of the first group plus sample proportion of the second, 1 minus the sample proportion of the second, all over N2, all right? So that is how we compute a z value of a proportion. Mind you, the z value that you compare it with to make a decision, it will depend on whether it is a two-tailed or a one-tailed. And it will also depend on the confidence level given, all right? Now, let me add something a little. Now, the denominator here, the standard error of two population proportions, okay, statistically, there could be another formula to find this. So I'm saying that the standard error of proportions, okay, there is another way to find it. So here we can employ a pooled estimator to find standard error of a proportion. Okay, so in a question, unless probably you are being asked to do, or unless you are probably being asked to use the pooled estimator, if you use this particular standard error, you should get the same answer. So the original standard error we know of a proportion, let me write the original one. The original one is the square root of P1, 1 minus P1 proportion, sample proportion, plus, over N1, plus P2, bracket 1 minus P2, all over N2, all right? Now, when you want to employ a pooled estimator to find the standard error of a proportion for two populations, okay? Mathematically, you should get the same answer as this formula, but then there's another way to do it. So sometimes the question will say, use the pooled estimator to do it. But if it doesn't, when you use this one, you get the same answer, all right? So when you want to use the pooled estimator, the standard error rather becomes square root of the pooled proportion into bracket 1 minus the pooled proportion. So 1 minus the pooled proportion. It's called pooled proportion because, pooled sample proportion because, as you can see, there's nothing like P1 or P2, it's just P, all right? So multiplied by 1 over N1 plus 1 over N2, okay? So this formula here, the one on the left is the same as the one on the right. The reason why you have to know the one on the right also is that sometimes when the question wants to be simple, or when the examiners want to make the question simple, they can give you just the pooled proportion so that you can compute it easily. So they may not give you P1 and P2, but they can give you the pooled proportion. When it happens like that, you have to use this approach here, the one on the right, to find the standard error. But mind you, the pooled proportion itself also has a formula. So the pooled proportion itself is sample size 1 times proportion of group 1 plus sample size 2 times the sample proportion of group 2, all right? All over N1 plus N2. So for me, if you are not given a sample proportion, if you use this approach, it means you have to compute the pooled sample proportion and send it back into this formula to get the whole standard error. But I believe the one on the left here is quite simpler, but you should get the same answer anyway. All right. Now let's look at the example here. Now, this example says that a critical component of a handled hair dryer is the motor heater. Company has recently created a new motor heater unit with fewer parts than the current unit. The company has decided to test samples of the old and new units to see which motor is more reliable, all right? The null hypothesis states that the new motor heater is no better than the old or the current motor heater. So in this question, the null hypothesis have been stated for you. It says the new motor heater is not better than the old motor heater, all right? Now let me explain what's the meaning of these figures here. The question should have done it, but it didn't. So let me give an explanation. So here is the average number of fails. Average number of fails. How many times the motor heater will fail, all right? Like these two. Okay, so like that is the average number of fails. How many times the motor heater will fail? Okay, how many times it will fail? All right, so that is the number of fails. Okay. Now, we are interested in knowing the proportion that will fail. All right. We are interested in knowing the proportion that will fail. So here, if the first motor heater in the new the question said we have a new one and then we have the existing one. So let's assume that N1 per the question says group 1 is the new motor heater, all right? The new unit. Then group 2 is the old unit, okay? Now for group 1, it says that the motor heater will fail 55 times. On the average, the motor heater will fail 55 times, okay? Then the sample size of the first group is the sample size of the first group is 250 times. Then we also have an old unit. For the old unit, the average number of failure is 75 times. And then the sample size is 200 and I think the same thing, 250 times, all right? Now, how do we compute the proportion that will fail? Okay, if this fails 55 times out of 250 times, means that the proportion 55 times out of 250 times, you will get our proportion of failure, all right? 55 out of 250, you get our proportion of failure. So that is 0.22. Then here, 75 times out of 250 times, you get our proportion of failure to be 0.30. All right, so these are our proportions. Proportion of failure of the new unit, then the proportion of failure of the old unit, okay? Now, the question says that the null hypothesis says that the new unit, that is machine 1 or unit 1, is not better than the old unit. The question said they want to test the null hypothesis that the new unit is not better than the old unit. That's the null hypothesis. The new unit is not better than the old unit. It's not better than the old unit. If this is the case, it means that, so this implies that the new unit will have a bigger proportion of failure than the old one. Because if the new unit is not better than the old unit, it means that the new unit will definitely have a bigger proportion of failure than the old one. And that is what the null hypothesis is saying. The null hypothesis says that the new unit is not better than the old. That means that the new unit should have more failure than the old unit. So here, the null hypothesis is that the proportion of failure, so here the population proportion of failure of the new unit is more than that of the old unit. If it is not better, it means that it will fail so many times than the old unit. Okay, if it is not better than the old one, it means it will fail so many times than the old one. So the proportion of failure is bigger than that of the old one. I brought the equal to sign because always it is your null hypothesis that you have the equal to sign. Even if it is greater than the or equal to it, the equal to must be part of the null, all right? Then the alternative is that the number of proportion of failure of the proportion of failure of the new unit is less. I mean, the opposite of the null is the alternative, okay? The opposite of the null is the alternative, all right? Now, here, the question says that the alpha is 0.05, which means that we are testing at 95% confidence. If we are testing at 95% confidence, it means that the critical Z will be equal to 1.645. The critical Z to be equal to 1.645. So let's draw our curve. We expect that so let's rewrite this null hypothesis and then the alternative. It makes it easier. So if this one crosses and comes here, the null hypothesis will be that P1 minus P2 is greater than or equal to 0. Then the alternative will be that P1 minus P2 is less than 0. I mean, when this one crosses and comes here, it will become a minus. And when this also crosses and comes here, it becomes a minus. So based on the null hypothesis is saying that P1 minus P2 is equal to 0, but the null hypothesis is saying that it should be greater than 0, all right? So if the middle here is 0, it means that we are looking for this portion. All this portion is an acceptance because we are looking for greater than 0. So it means all this portion is the acceptance range. But obviously we allow for a little less because of sampling error. So it means that everything now here becomes the acceptance rate. But the critical Z, because it's at the left-hand side, it will become negative 1.645. The critical Z becomes testing at 95% confident, but on the left-hand side. So the critical Z becomes negative 1.645. Now our duty is to compute. Our duty is now to compute our Z, and then we will compare it to the critical Z, and then we will reject or we will fail to reject. So remember, the critical Z is sample proportion of the first group minus sample proportion of the second group minus population proportion of the first group minus population proportion of the second group, all over the standard error. So let's use the first formula for the standard error, the original formula. So proportion 1 into bracket 1 minus proportion 1, all over N1 plus proportion 2, some proportion 2, sorry, bracket 1 minus some proportion 2, all over N2, okay? So always the population proportion, as we already know, it's always hypothesized to be 0, all right? So that portion will be 0. Like what I've circled here, it will be 0. So here, sample proportion 1 is 0.22, that of sample proportion 2 is 0.30. So here you have Z is equal to 0.22 minus 0.30 minus 0 all over the square root of sample proportion 1, which is 0.22 to bracket 1 minus 0.22. The sample size for each group, per the question, the sample size is 250, okay? So plus the other part here will be 0.30 into bracket 1 minus 0.30 all over 250. So when you punch the numerator, you are going to get 0.22 minus 0.30. You are going to get negative 0.08. Okay. And then when you punch the denominator, all right, if you take time and punch it well, you are going to get approximately 0.0391. Okay. Approximately 0.0391. If you punch it very well, you're going to get approximately 0.0391. So when you divide, you're going to get approximately negative 2.05, okay, rounded, negative 2.05. So this is what you get as the computed Z. But if you want to use the other formula for finding the denominator, the other formula for standard error, that formula is pooled proportion into bracket 1 minus pooled proportion times 1 over N1 plus 1 over N2, okay? And remember, the pooled proportion itself is equal to N1 times proportion 1 plus N2 times proportion 2 all over N1 plus N2, okay? So this would have given us 250 times 0.22 plus 250 times 0.30, because the P1 and P2 are here. I mean, they are here, all right? All over 250 plus 250, all right? So when you punch this, you are going to get 0.26. So 0.26 is the pooled proportion. So let's bring it back into the formula here. So this will give us the square root of 0.26 into bracket 1 minus 0.26, okay? Multiplied by 1 over 250 plus 1 over 250, all right? So if you punch this very well, it's like all the three are multiplying. It's like this times this bracket times this bracket. So if you punch it very well, you are going to get approximately 0.0392, okay? Which is the same as the denominator here, like 0.0391, 0.0392. I mean, the answers are similar, all right? It's just because of rounding error, okay? So what I'm saying is that the standard error of two population proportions, you can use this formula, okay? This standard error formula here, like the denominator, you can use this one, or you can use this one as a standard error. But mostly, the second one is preferred, all right? Mostly in exams, the second one is preferred. Or it may be a little more accurate than the first one, all right? But the second one, you have to compute the pooled proportion standard deviation, then go send it back into the formula. That makes it a little difficult. Okay, now, whatever be the approach we used, we are having a Z value of negative 2.05. So when you bring it into our curve, Negative 2.05 will be somewhere here because it is more negative than negative 1.645. So we have negative negative 2.05. So since it falls into the rejection region, we are going to reject it, all right? So our conclusion will be that the computer Z value of negative 2.05 is less than the critical Z value of negative 1.645, right? So we reject the null hypothesis. And please, whenever you are rejecting the null hypothesis, you conclude using the alternative, all right? Let me say it again. Anytime you reject the null hypothesis, you conclude using the alternative, okay? So the null was that the new machine is not better than the old one. That was the null. The new machine is not better. The number of failure from the new machine is more than the old one, or the new machine is not better than the old one. That was the null. Then the alternative is that the new machine is better than the old one, all right? So we conclude based on the alternative because we have rejected the null. So we reject null hypothesis and conclude that the new machine is better than the old one. So please, I have not really taught the conclusion up until this point, but for all the other hypothesis testing we have done, if you want to conclude, always, when you fail to reject the null hypothesis, your conclusion will be the null hypothesis. But when you reject the null hypothesis, your conclusion will be the alternative hypothesis, all right? When you fail to reject the null hypothesis, your conclusion will be the null hypothesis. But when you reject the null hypothesis, your conclusion will be the alternative hypothesis. All right, so thank you for staying with me. And in the next video, I'm going to teach on hypothesis testing and estimation for population variance. All right, so kindly like the videos, share, subscribe, and let me hear your feedback. Thank you.